All right, so here we go with our 8-7, Chapter 8, Section 7 notes for Algebra 2. All right, you can find my copy of the notes I'm filling in right now on HeadRush, but you can also find a blank one to start filling in or right next to on HeadRush as well. So go ahead and log in there and get your copy or follow along and take notes. So as we look through this, we're trying to fit to a normal distribution. So jumping ahead, normal distribution is this bell curve here that we like to talk about a lot in statistics. So we are going to use tables to estimate areas under normal curves and recognize data sets that are not normal. So again, we're going to estimate actually probabilities and kind of talk about how data might fit this bell curve and may not. So on that note, here's our first large section. The idea of a standard normal value is if a random variable x is normally distributed with a mean, yes, this is the letter mu in Greek. So if you're thinking that I am meowing like a cat, I kind of am. All right, that's a little cat. Meow. Okay. All right. And a standard deviation of this here is our kind of cursive O looking symbol, but it is our lowercase sigma. So there it is. Then the standard normal value of x is given as the following formula. So z represents our standard normal value, and that just tells us where we are placed on this graph here. So this graph, of course, can be broken up into all types of numbers like 0.6 and 0.1 and whatever. But these are technically the groupings that we use when we're talking about this. Because remember that an average, when we talk about a bell curve, has 3 standard deviations above that. And so when we look at the values that we are doing here, there's going to be this 0 value. The 1 would technically be here. The 2 would be here, and all the way at the end where it potentially meets would be your 3. So 3 standard deviations away from the mean, which is the center, represents all of the possibilities of a normally distributed data set. So when you do that, you're going to take your x, which notice it's not x bar, but that's kind of what they're hinting at here. And our x value is going to be kind of that mean that is given in the problem, but not the one that is technically the mean of the data, because mu is actually the mean of the data set. The one that's calculated if you were going to add them all up. Okay, so this is going to be a difference than the previous z score that we were talking about, because this one is going to matter if you're negative or positive. So make sure that you are doing that mean that's given in the problem here, like the one they're trying to reach, and then the mean of the actual data set is right here. And then down here is our standard deviation. So, which is up here. All right. Just again, reiterating the area under the normal curve between x, which is a, and x, which is b, is equal to the area between the standard normal values of a and b. So basically, they are just saying that when you plug in these values, if you have this distance between this shaded region here and over here, this is actually kind of 100% likelihood. All right, and so this shaded part over here is representing that if this were the data set value, if this was the z-score, that you are having that percent below you in the scoring and this percent above you. And so if you kind of think of percentiles, this is where that comes from. So if you're told that you're in the 78th percentile or whatever it happens to be, that means that 78% of the people that took that test or did that exam, whatever it happens to be, were under where your score was, but then 22% are above where you were. So that's kind of where we're talking about that. So this here is telling you your area. And so if we actually think of this probability as the area underneath this curve, if we were able to kind of find this triangle area and maybe this triangle and then this rectangle or whatever it happens to be, this is actually the area, which is actually the probability. as well. Okay, so if we are talking about the area under this curve, we're actually talking about it being 78% likely to be this z value here. So these are all probabilities, and they're also technically the area under this curve, which is totally calculus and it's totally cool. All right, so that's that. This table will be provided on the test because you are going to have to reference it, so that's not going to necessarily need to be memorized, and this standard normal calculation will also be provided as well. So just something to recognize. All right, so we're going to see if we can apply this. We're going to find a joint and marginal relative frequency here. So Jamie can drive her car an average of 432 miles per tank of gas with a standard deviation of 36 miles. So it kind of depends on, if she's running her heat or air conditioning or whatever. Use the graph to estimate the probability that Jamie will be able to drive more than 450 miles on her next tank of gas. Now remember that anytime that we say more than or less than, we are talking about 1 minus what's happening. So taking a look at this distribution, which is on the next page, we are looking for the fact that she is, let's see, average 432. So this is 430. So 432 is kind of here. But she is trying to talk about 450 gallons. Let's look miles per gallon. So that's actually this value right here. So we are trying to find out what is the probability that Jamie will be able to drive more than 450 miles. So if we kind of look at how this is distributed, we are trying to find the probability that she's going to be able to be up in this range. All right. So if we take a look at how likely it is that that's going to happen, of course, it's over half of the, it's less than half because this would be the middle here would be half at 430-ish, 432. And so if we start to distribute the area under this curve, because the percent that we're talking about for probability is 100, or technically 100%, which is 1. And so each square on this grid is actually 0.01 of a likelihood. So this square, for instance, is 0.01 of a likelihood. So if we take all of these squares that I've just shaded in and add them all up, it turns out that there are about 31 of these squares under the graph. So the probability is about 31 times this 0.01, because there are about 31 squares, kind of adding and taking away. This one's just more of a concept than an actual number that we're looking for. And so it's going to be 31% of like the 100% that she drives around, that she's going to get a likelihood the time she will get or be able to travel over 450 miles. So perhaps she is driving at maybe optimal speed, so she might be doing some freeway driving. She's not using heat, she's not using air, and so she can kind of get into here, but that's only 31% of the time. Most of the time, she's going to fall within this 432. And so if you're going to advertise for this car, that's kind of where you would say that your gas mileage is. But technically, you could say that it's up here. You would just have to disclose, hopefully, that it is very unlikely that would be one of the gas mileages that you can take. So this one, again, just a concept question, kind of asking you, do you understand that this is talking about the area under the curve, the fact that this is her average, but we're trying to find out 450, and her standard deviation was 36. So technically, we could use the formula that we had in the previous problem. And so if we wanted to apply that, we could take out, let's see, her average, which is the one that's calculated, but this is the one that the problem is presenting. So we're going to go ahead and take 450 and subtract 432. Divide that by our standard deviation of 36. And we get a z value of 0.5. And so that's telling us, based on this chart right here, that it is half of the time that we would be getting this 432 of the miles per gallon, miles on our neck is gas. Anyway, concept question. So now getting to the direct mathematics calculation. Let's say that the scores on a test are normally distributed. So if you ever hear someone say that the test was scaled in any way, most of the time what the teacher is actually trying to do is make it fit that normal curve. And so they're saying that potentially this highest value would not happen that much, and that most of the students would be getting this C range here, which if you kind of look at scores in high school is actually a leaning bell curve. And so a lot of times it's actually more like that. Just because of the way that things are scored and the way that schools look at these scores, especially colleges. Most of the time it's skewed to the right here. But anyway, just a good thing to know. So what's happening is a score on a test is normally distributed with a mean of 160 and a standard deviation of 12. And we want to estimate the probability that a randomly selected student scores less than 48. So that means that 48 is our x value in this formula that we had before. And so we are going to put in 148. The mu value is the one that's actually calculated, and they said that it was 160. And then our standard deviation is 12. So if we go through and solve that, it turns out that that's going to be -1. And most of the time we are going to end up with a result that is within here, this range, okay? So if we reread the problem, just making sure that we understand, estimate the probability that a randomly selected student scores less than 148. So we are talking about on this normal distribution curve, how likely it is that it is below 1. And so again, this is your area. And so from -2.5 on is 0.01 of a likelihood. So 1% likely, 2% likely, 7. But once we get to this area, below it, there's 16% of the bell curve filled in. So the probability the randomly selected student scores less than 148 is going to be 16% of the time. And again, that is because 1 on the chart becomes 0.16. And so 0.16 represents the area, which represents the probability. And so therefore, we are saying 16%. Let's say that they had switched this and said scored more than 148. If we were going to do more than, we would need to take 1 minus 0.16. And so we'd be left with 0.84, which means that 84% of the time they're going to score over 148 on the test. So again, just an idea of how you might change this and use this diagram the opposite way. All right. Part B now wants to figure out what is the likelihood that you might score between 154 and 184. So in order to do that, we're going to find 2 z values, and then we're going to subtract the pieces or the probabilities that are there. So we're going to use one z value using 154 as our value, and we are still using the previous mu value of 160 and 12 as your standard deviation. So taking a look at this first problem, we're going to be doing x minus mu over our standard deviation. And so again, the x in this first option is 154, but the mu, or the average, was 160, and the standard deviation was 12, again, in the previous part of the problem. And then the other z is going to come from the new x, which in this case is 184 minus 160 over 12. And so this first z is going to become negative 0.5. The second z is going to become 2. And so when we look at our chart and we look at negative 0.5 and 2, we are talking about being between those two values. So what's the likelihood to be between 98% likely and 31% likely? We would just take them away from each other. So 98 minus 31 gives us the likelihood of 67, or 67%. All right. So again, that means that 67% of the area of that normal curve is being filled in to score between 154 and 184. All righty. Now, the next thing that we are going to do is try to fit data to a normal distribution. So basically what's going to happen is a lot of times in science, they're trying to figure out, is this a normal distribution? Is this what would have normally occurred, or is there some sort of outlier going on? So what you would do is you would take all of this data, and this happens to be the lengths of 20 snakes at a zoo. Super. And you are going to note that the mean, so you don't have to add them up or anything, is 34.1 inches. Standard deviation is going to be 10.5. And we want to see if the data appears to be normally distributed. All right. So taking a look at this one. The idea here is that we are going to fill in a table, which I don't have. So here is a piece of paper. So on every test or quiz, I'm going to give you a table that kind of looks like this. So you're going to have a z value, and it's going to be the z values from the chart that we had just talked about. So there's going to be a -2, -1, 0, a 1, and a 2. And we're going to break up our data into these areas. On that chart, of course, you have the probabilities, or the areas. Again, I don't love to call it area because we usually see it more as a probability. And so -2 is 0.02% of that bell curve. 0.16% is going to be -1 and below. 0 is our halfway point. 1 is 84% of the way, and 2 is 98% of the way, because it does go to 3, which would be 100%. So then we have our x value, which is going to be here, and we're also going to have values below z, so we're kind of having a running total in here, and this is going to be a column with the projected, so what we guess it's going to be based on normal distribution, and the actual. So the idea is that we're trying to find out, if we normally distribute these lengths of snakes, are they going to follow this projected outcome, or are they not? And so if they do, this is a set of normal snakes, okay? And we can use that word lightly there. And then that's only if the actual follows it. So taking a look at how we calculate this, the halfway point is going to be our mean. So this halfway point right here is 34.1. All right, and again, that came from right here. It said the mean was that. It also says that our standard deviation is 10.5, which means that, remember, your standard deviation is going to move out from this center of the data set. So if I take 34.1 and add our standard deviation of 10.5, we should be talking about a length of 44.6 for up to 84% of the snakes. Then if we add another 10.5, because again, that's your standard deviation, you're going to get 55.1. And so again, this column here is to add and subtract your standard deviation. All right, and these two pieces are given in the table. Okay. So I've added 10.5, so now I'm going to subtract 10.5 from 34.1 and get 23.6. And then subtract another 10.5 and get 13.1. Alrighty. And so if we take a look at our data of the fact that there are 20 snakes, we assume that halfway through there should be 10. So this is going to take our area, or our probability, and multiply it by the number of data sets. So we're going to take the area times our n, and in this case our n is 20 snakes. This will allow us to figure out how often we should have an actual amount of snakes. So hopefully we have, for instance, 10 snakes that are below 34.1 inches in length. So if we want to go to the first standard deviation below that middle there, we're going to take 0.16 times 20, and we're going to get 3.2. But of course, we're not going to have 3.2 snakes, so we are going to just say 3. Okay. And then we're going to take, for this one, again, we're taking our area, 0.02 times n, our 20. And it turns out that 0.02 times 20 is 0.4. And again, we can't have 0.4 of a snake, so we round down to 0. So always take this area and multiply by the total number of snakes. So now I'm going to do 0.84 times 20. And hopefully there should be 16.8. But again, 16.8 snakes don't exist, so let's go with 17. And then this last piece here, I can do it, but we're going to get very close to 20. So that's the idea. So hopefully when I look at this data that's in this table, it follows this range. Otherwise, we have a lot of very small or very large snakes, or whatever it happens to be. So taking a look at the table, I have a 43. And so if we look at this, that means that this, it's not in this range. It's not in this one. The 43 is going to be almost up to the 44.6 in length. So we are going to count that from 0 to 44.6. So one of those is in there. We have a 22 in length as well. And so again, if we look at these ranges, if I was going to say, are they in the almost 13.1 length? No, but they are between that and 23.6. So we're making a little tally mark there. 39 inches is not quite 44 yet, so we're going to put it in here, but it's not quite 34, so put it in there. And then 38, again, is between these two, so we put it in the 44. Our next snake is 41 inches, so we're going to go ahead and put that one in this range again. The next one is 15, so that's going to go in this range. 39 should go in this range. And 12 should be up here. The next set of snake lengths is 37, so that's in this range. 40 is going to be in this range again. 38 is in this one. 39, also in this one. 16 is in this range. 45 is between 44 and 55, so that's going to go up here. 43 is in this range, so now we have 10 in that one. And 18 is in this one here. Almost done. We have a 39. Again, that's between 34 and 44, so that's going to go here. A 38 is also between 34 and 44, so that's going to go here. A 37 is in that range, and a 43 is in that range. So taking a look at what we have here, we have one snake that is within this range, but the actual amount of snakes that should be in that range out of this set of 20 snakes should actually be none of them. That's only off by 1, so that's not so bad. Once we get to the next total, which says that now up to 3 snakes should be in this, we actually have already counted 5 snakes. So again, we are starting to get a little bit more off than just one snake, which is 1/20th of our population here, so 5. Then the next piece is very interesting because it's predicting that there should now be 10 snakes counted in length, but we still only have 5 because we've added none from there. So we're definitely off of the mean, and we're definitely off of the count that's happening. After that, it looks like we are going to add 14 to this 5, so now we're at 19 of our snakes counted, and that's not so far off from 17, but 5 was definitely off, and this 5 was starting to get off. And then, of course, this last one is 20 total snakes. So when we take a look at what's projected and what actually occurred, this right here tends to be very scary, especially when you see this in just one of the jumps here from 5 to 19. There should have been only a jump of 7 snakes, but there were 14. So clearly this is not a normally distributed data set, and so that's what you were supposed to determine. So the data does not appear to be normally distributed. There are only 5 values below the mean, and of course there should be half of them, 10. So not normally distributed. So our answer again is that it's not normally distributed, but the way that we got this table was from our z-chart, so that was this piece, our mean, and then going up and down the standard deviation. The projected was our area times our population, so area times our population of 20 snakes. And then this was our tallies of how many are between 13.1 in length and 23 and 34. And so we took our tallies there to see if it actually fit this normal distribution, and it did not, so it's not normally distributed. So we've got a lot of apparently very large snakes in this population. All right, so those are the pieces that you're going to use to do the assignment. So kind of in review, hopefully we use tables to estimate areas under normal curves and recognize that data sets may or may not be normal. So one of the key ideas was being able to find this z value to then be able to estimate what likelihood that average is. And then we also had this table on this last page where we were trying to identify if the curve or the data was normally distributed. So there you go. I would like you to try to work through the 8-7 assignment on your own. Remember that I'm not looking at what you're doing, so at this point you can guess, and it's okay to be wrong because then you check it with the answer key. And if you can't work it backwards from that, then you would go to the next video, which actually has me working through all of the homework problems. So go ahead and try the 8-7 assignment, and remember that once you're done, you submit it to HeadRush, because otherwise I don't know that you did it. All right.